Yes, sir.
Okay. Now we are already discussed about cyclic group. What a cyclic group means? Every element of Z can be expressed as the power of A. You see, group G is called cyclic. For some A belongs to Z. Every element X belongs to Z is of the form. Here they should see the value. Here a to the power n you are getting where n is a integer. Okay, and then G is given by this symbol. That is, the set is given by a to the power n as a belongs to z and n belongs to z. And here E is called a generator of z. Okay, E is called the generator of z. And already we have taken here the multiplication is the binary operation for this diffusion. Now, if the addition is there, then you are writing A is equal to cyclic group generated by A equal to Na. You are writing where A belongs to Z and belongs to Z. Now, the cyclic group may have more than one generator. That means there is no unique element is existing here. There may contain more than one generator. There is not restricted to one. That may be there are more than one generator. Now the multiplicative group, what are taking one omega. What is the group? This is the cube roots of unity. Okay, one omega square is cyclic. Here the generators are omega and omega square because you see you can express one as omega cube and omega to the power 1 omega square are writing. That means the power of here you can write 1 as omega cube and some element of that and omega to the power 1 omega to the power. That's why omega is the generator and similarly omega square to the power also you can exist all these elements you can write omega square to the power 1 omega square to the power 3 and you can write omega just like this is we can express all the elements of this set as the powers of omega square. That's why omega square is also a generator. Okay. Similarly, if you take the fourth roots of unity, what is that? The set containing 1 minus 1 I minus I. Fourth roots of unity is called. There are two generators are there. One is the I and the second one is the minus I. Here also same. The elements of Z can be expressed as the power of I. That's why that is called I is the generator because you are expressing every element of G as a power of I. Therefore, what we can say that is I is the generator. Similarly, you can express the elements of G as a power of minus I. Okay, that's why minus I is called a generator of Z. Okay, that means we are more than one generator is existing. There are two generators. One is the I, second one is the minus I. Okay. Now you see the properties of cyclic groups. You see the properties of cyclic group. Now the statement itself says here every cyclic group is abelian. That means the cyclic group is abelian that we have to prove. Now, what is meant by cyclic group? You see, G is equal to A you are taking. That means G is generated by A or A is the generator of Z you are taking. That is a cyclic group you are taking here. Now, you are taking any two elements. You see, cyclic group means it is a group. It exists, it satisfies all the properties. You are taking any two elements of, you are taking any two elements of you are taking any two elements of G and you are writing as the power of M because A is a generator, we are writing X equal to Y is equal to you are writing for some integer M and N you are writing here. Now XY you are taking. That means you have to prove here the commutative law. If you prove here, then you can say that is abelian. The commutative law, if you obey a group means that is group itself. And here you see, just you have to prove the commutative law. We are not proving the remaining four properties. Okay, just you see, this is a cyclic group. We are writing here, we are taking two elements. Take the product of that, we are writing here a to the power m plus xy equal to y x to the power n. Is it not? X equal to a to the power m, y is equal to a to the power n. By the laws of indices, you can write a to the power m into a to the power n as a to the power m plus n. And m is the integer, n is the integer. In case of integers, m plus n equal to n plus m, you can write. Therefore, you are writing a to the power n plus m equal to a to the power n into a to the power m. You are writing. Okay. What is a to the power n? Again, you see that is equal to y and a to the power m means you can write y x. That means you are writing xy equal to yx. Therefore, the cyclic group, the G is abelian. That means cyclic group is abelian of proving. Okay. Now, what you got? Every cyclic group is abelian. Okay. The next one, if A is a generator of a cyclic group G, A inverse is also a generator of A inverse is also a generator of G you are writing. Okay. First you take the generator. A is a generator of cyclic group G is there. By using that, how to prove A inverse is also generator of Z. Okay. Here we are proving G is equal to A you are taking. That is A is a generator of Z. You are taking an element of G that is X belongs to Z. X is equal to can express as the power of M. Now the same power for M of course M is a integer, so the same power you are expressing as power of A inverse because you see you can write a to the power m as a to the power minus 1 to the power minus m, because a to the power m to the power n you can write as a to the power mn. By using that fact here you can write a inverse to the power minus m. Okay. Now you see minus m means there is some integer. Minus m is some integer. That means you can write a inverse to the power n you can write here. A inverse to the power n. That means where n equal to minus m you are writing here. Minus m is another integer. Okay. N is another integer. Now you see the x as you are expressing as the power of a, as the power of a, the same is also expressing as the power of n. Okay, that means if the element is expressing as the power of this, the same is also expressing as the power of a inverse. Okay, you can express as the power of a inverse. Okay, now that means everything you are one element is expressing the power of m, the same is also expressing the power of a inverse. That's why that is called a inverse is also generator of g. That means now both are generators. One is A is generator means A inverse is also generator. Okay. Now the next one here you see. Okay. Now if G is equal to A, the symbol indicates G is generated by A is a generator, and G is a cyclic group. Then it says A is the generator of G, and here order of G is equal to order of A. That we have to prove. Okay, we have to prove order of G is equal to order of A. Now already we have taken G is equal to A, that is A is the generator of G, and here order of A is equal to, we are taking some order, we are taking here N, we are taking order of A equal to N means according to the definition you can write A to the power N equal to E, and you will take some element a to the power s not equal to e for 0 less than s less than n we have taken. This is how to remember it. A to the power s is not equal to e. That means other than the identity element you are taking here, then you are writing 0 less than s less than n. Now, s is greater than n. Here s is less than n is there. Here if you take when s is greater than n, you can write s equal to n cube plus r. By using the remainder theorem, you can write here s is equal to n cube plus r, where 0 is less than or equal to r is less than n. Okay. Now, a to the power s, raise the powers by, here you take the base as a and you raise the powers by this, and then here you raise the powers by the same. You should raise the powers by s, here raise the powers by the same. Now a to the power n cube plus r you are getting here, a to the power n q into a to the power r, a to the power n equal to e to the power q is e into a to the power r, you are getting a to the power s is equal to a to the power r you are getting. That means that there are exactly n elements in the group G generated by AR 0, where 0 is less than or equal to r is less than n. Therefore, n and only n distinct elements in the group, in the cyclic group is there, that we are writing is Z is equal to cyclic group generated by A. That's why order of Z is equal to n. The order of the cyclic group is also same as order of Z. You see, order of Z is equal to n you are getting here. There are exactly n elements that we are proving. That means if you take a to the power s, that is equal to, here you are writing the other element a to the power r. There are exactly n elements in the group. That's why I am writing here 0 less than or equal to r less than n you are writing. Now n and only n distinct elements in the cyclic group G is equal to A you are writing. Order of G is n. Now you write order of the cyclic group is equal to order of A. Therefore, or you can say order of G equal to order of E. Order of G is equal to order of E. Okay. Just you see here in this one we are taking some element. This is you have to remember. The remainder theorem you have to remember here. By taking that here you are writing this, and here you are writing order of E equal to order you are taken. Now order of Z equal to n you are writing. Now Z is equal to cyclic group A you are writing here. Order of A is equal to, here order of the cyclic group is equal to order of A. That's why you are writing here. The order of cyclic group is same as order of the generator. Okay. Now, the next one, you should see here, every group of prime order is cyclic. Already you know what is meant by prime number. The divisors of prime number are 1 and the same number itself. There are other, or doesn't exist here. The group of prime order is cyclic. Now, order of G is equal to P. Order of G equal to P, where P is a prime number. If suppose A is not equal to E, there is some element that is not the identity one that we are taking, it belongs to Z. Now, consider a cyclic group H generated by E. Okay, you are taking other than the identity element, and you are writing here H is equal to the cyclic subgroup you are taking here H, then that is generated by A. Now H is equal to the writing, that is A is a generator of H. If order of H is greater than 1, order of H is greater than 1, then since H is a subgroup of G, then by Lagrange's theorem, that is you can write order of H divides order of G. by Lagrange. This you have to remember here. H is a subgroup and G is a cyclic. G is here every group of prime order is cyclic. Here you see order of G equal to P. P is a prime number. You are taking an element of that belongs to Z. You are taking here and cyclic to subgroup. You are taking H. Cyclic subgroup H. Now here H is equal to A. If you take order of which is greater than 1, then you are writing H is subgroup of G. Then by Lagrange's theorem, this you have to remember. Already you know order of which divides order of G is the Lagrange's theorem. Then here you can write order of which divides. What is the order of G here? G is P, prime number. Order of which divides P means you can write either order of which equal to 1 or P, because already the divisors of the prime number is only the number 1 and then by itself. That's why you are writing here order of which must be equal to 1 or P. If order of which is greater than 1, that is order of which is not equal to 1, then you can write the other option is what? There are two options. One is 1 or P. It is not greater than 1 means it is not equal to 1. Therefore, order of which is equal to P. Now, already know what is P here. Order of G equal to P. Now, you are writing order of which is equal to order of G. Remove the was order symbol on the other side, you get which is equal to G. Therefore, H is cyclic means G is also cyclic. Therefore, every group of prime order is cyclic. Just here remember the Lagrange theorem statement you have to know. Then you can write this easily. Okay. And then if G is a finite group of order n, if G is a finite group of order n, if G is a finite group of order n and contains an element of order n, then G is cyclic. Here order of G is equal to n you are taking, which implies H has n elements. That is the number of elements of the group G are n. Then A belongs to G be an element of order n. Order of A is equal to n, order of A is equal to n, then you are writing e to the 4 n equal to by using the order of the element of a group. You consider a cyclic subgroup of H of G generated by A. That means you are taking a cyclic group of the G you are taking, cyclic subgroup H of G you are taking, and H is also generated, H is generated by A you are taking here. Now order of which is equal to order of A. Now order of which is equal to what is the order of A here? That is equal to n, because a is an element of order n you are taken, therefore order of A is equal to n. Now you see in the previous theorem you got order of H is equal to order of G. Now from that one you can write order of H is equal to order of G. Now H is equal to Z you can write. Order of, because n is equal to you are writing order of Z you are writing here, therefore order of H is equal to order of Z. Now if you remove the order sign, okay, now if you remove here you get H is equal to G, G is cyclic, G is cyclic, okay. Now the next one, here you should see Euler's function. Okay, you see, say cyclic group of order n has pi of n number of generators. What is meant by pi of n? Cyclic group of order n has pi of n number of generators. What is meant by pi of n means you see Euler's function is the pi of n, and pi of n that represents the number of positive integers less than and relatively prime to n. That means pi of n is number of positive integers less than n and relatively prime to n. That is called the Euler's pi function. That is pi of n. Now, what I have to prove here? A cyclic group of order n has pi of n number of generators. Okay. Now the proof here G is equal to A you are taking A. That is the elements of G are generated by A, or A is the generator of G. Now order of G is equal to n you are writing. Order of A is equal to n. Order of A is equal to n means you are writing. But definition of order of n, we can write a to the 4 n equal to E. Now here you write order of G is equal to n is there. Okay, that is now you are writing G has an element. Okay, that is obvious. Okay, now G is equal to A you are writing, and here the limits of G you are writing as A square, A cube, so on to E to the 4 n equal to E, because the last one E to the 4 n equal to E, because order of equal to n means you are writing A to the 4 n equal to E. The elements of the form E to the 4 k, where where k n equal to 1, that means are also generator of G. That is also one of the properties of that generator of G. You see here the elements of the form made to the 4k where k n equal to 1 are also generator of G. That is according to the some property you are writing here. Now By the above definition, the number of positive integers less than n and relatively prime to n is pi of n. That is already they are taken here. Starting with the pi of n means you are taking the definition. You are taking the your pi function. Now there exists pi of n number of elements of the form a to the power k. Hence the number of generators is equal to pi of n. Okay. Now order of a is equal to n. Then there exists pi of n number of generators. Pi of n number of generators. This you have to remember this statement. The elements of the form a to the power k where k n equal to 1 are also has generator of are also the generator of the. That's why we are writing here the same the number of positive integers less than n and relatively prime to n is pi of n. Now there exists you are writing pi of n number of generators. The number of generators is equal to pi of n. Now order of the z that is equal to order of a is equal to you are writing n. Then there exists pi of n number of generators. Now we go for the problems. Show that the multiplicative group of cube roots of unity is cyclic. Now what we have to prove here? The multiplicative group of cube roots of unity. 1 omega omega square is the elements of that cube roots of unity. That is multiplicative group. G is equal to you are taking the set containing 1 omega omega square. Now you have to prove uh, show that the multiple indeed is cyclic. Now here you see G is equal to you are taking that one and the element of that elements of G that you are expressing as the power of omega. You see omega to the power 1 is omega square, omega cube 1 you are adding. That is every element of Z can be generated by omega belongs to Z. That means every element of Z you are expressing as the power of that omega. Now what we can say G is equal to omega. That means G is generated by omega or omega is the generator of Z. Therefore, what we can say G is cyclic. Okay. Now, similarly, you can see omega square to the power 1 is omega square. Omega square square means we are getting here omega to the power 4, a to the power m to the power n, you are writing a to the power mn. Then you are writing here omega cube into 1, omega cube into 1. Then here you see the same that is equal to, if you simplify omega cube into omega means you get here 1 into omega that is equal to 1 omega that is equal to omega. And similarly, if you raise the powers by 3 for omega square, you get here omega to the power 6 that you can write as omega cube into omega cube that you can write as 1 into 1 equal to 1. That means what we can say, the elements of G can be generated that you can express as the power of omega square. That means what we can say, G is equal to omega square is also cyclic. That means omega square is the generator of G or the elements of G are generated by omega square. That means there are two generators you are getting. One is the omega, second one is the omega square. Okay. Now the next one, prove that the multiplicative group of four roots of unity is cyclic. Already I have taken that. You see, where a multiplicative group means here I and minus I, there are two already taken there. For that, the element I one you can write as I square to the power square you can write. Similarly, here also I square equal to you are writing. This is I to the power 1. Here you are writing I square into I cube you can write there. I cube is equal to minus I. Therefore, what we can say I is a generator. Similarly, you can express the elements of G as the power of minus I. Therefore, there are two generators again. One is the I and another one is minus I. Okay. Now the next one, prove that any group of order 3 is cyclic. Prove that any group of order 3 is cyclic. Okay. Now, here, the group of order 3 must contain only 3 elements. The group of order 3 must contain only 3 elements. Every group must contain identity element. That is obvious. Identity group means there must be definitely the identity element will be there. Okay. That means that you are taking as E. Now, A is an element, then A inverse must also be the element of any group. Okay. That means inverse is also existing. A belongs to the A inverse. Now, the group of order 3 is equal to, you are writing A inverse. Okay. Now E equal to, you can write E equal to, because you see this is the multiplicative group you are taking here. Multiplicative group you are taking here. Here you see E equal to A to the power 0 equal to 1 you are writing, that is called the, here you are writing as the power of E. Now A you can write as A to the power 1. A inverse we can write as A to the power minus 1. That is what we can say. Every element of Z you are expressing as the power of A. Therefore, A is a generator, that's why you're writing here. G is generated by A, or A is the generator of Z, that's why you're writing here. This is G is cyclic with generator A. Now, similarly, already you have taken the theorem, you will see that there you have taken every element of, if A is a generator of the A inverse is also a generator. I have taken already, will see the property. Now, the same you are writing. E is equal to, you are writing A inverse to the power 0, A is equal to A inverse to the power minus 1, A inverse equal to A inverse to the power 1. That means Every element of that you are expressing as the power of A inverse. That means what we can say A inverse is the generator of that Z, or G is generated by A inverse. The same property already seen the property there. This is the three elements are there. Then you can say here that is group of order 3 is cyclic. Okay. Now here the next one, show that an additive group of integers modulo 4, that is Z4 plus 4 is cyclic. Already you know Zn means how you are writing residue modulo, you are writing, you see here Zn means you can write 0 1 to so on to n minus 1 you are writing. Here you see Z4 equal to 0 1 2 3, that means n minus 1 means the last one is 4 minus 1 equal to 3 you are getting here, starting from 0 n minus 1 you are getting. Okay, now A plus B, the meaning of the meaning of A plus B means we have to add A and B and we have to divide with 4 so that we will get the remainder that you have to write here. Okay, the remainder obtained by adding and dividing with 4, that you have to write. Now you see 0 means how you can write, you have to you are taking 1 as the generator here, 1 plus 1 plus 1 means you have to write 4 times, divide with 4 means the remainder here will get 0. Okay, you see here 4 into 1, that means n into 1 we are writing where n equal to 4 you are adding here, n equal to 4 into 1. Okay, NA you are already taken a to the power n you are writing in case of multiplicative group, NA you are writing in case of additive group. Now 1 equal to 1 you are writing 1 into 1, n into 1 you are writing n equal to 1. Similarly 2 means 1 plus 1 you are writing 2 into 1, n into 1 you are writing n equal to 2. 3 equal to you are writing n dot 1 is equal, n is equal to 3 you are writing. Now every element of the Z4 is generated by 1 because you are repeatedly you are adding 1 plus 1 plus 1 and you are getting mm, the remainder equal to 0, 1, 2, 3. The all the elements of the group you are getting here, Z4 you are getting here. That's why 1 is the generator of Z. Now the next one, the same within the same you can write here Z4 equal to 1 is cyclic. Okay, already you know the number of generators may be more than one. There is a possibility of getting more than one generator, and here you see you are taking the first case you got here. One is by repeating you are getting, that is you are getting cyclic group you are getting, one is generate Z4 generates. Now you take three also, you can check it, you take two whether it is a generator or not. There is not generator. Okay, two if you repeat you don't get the result cyclic. Okay, from one also you don't get that cyclic. Now here if you take 3, if you repeat here, for 3 plus 3 is 4, 4 plus 3 is, if you 3 plus 3 is 6, if you divide with 4 we get 2 is the remainder. Again you add 3, 3 plus 3 plus 3 means you get here 9. If you divide with 4 remainder is 1, that is not equal to 0. Now again we add 3, you get here 3 plus 3 plus 3 plus 3 means you get 12. 12 if you divide with 4 you get 0. Okay, we have to go on repeating until you get the elements. Okay, now this you can write as 4 into 3, the n into 3, you can write here 4 n equal to 4. Similarly 3 also, you see 3 plus 3 is 6, the remainder if you divide with 4 you get 2, again if you add you get here 9, 9 if you divide with 4 the remainder will be 1 you are getting, that's why you are writing here 1. Similarly here you see all the elements, by repeating here you are getting all the elements 0, 1, 2, 3 you are getting, that means what we can say 3 is a generator of Z4, that means Z4 equal to 3 you are writing, that is 3 is the generator of Z4 or Z4 is generated by 3. That means how many generators totally you are getting here? You are getting two generators. One is the one and second one is 3. Okay. You are here you see one is not a generator, 2 is not a, oh, sorry, 0 is not a generator, 2 is not a generator, but 1 and 3 they are the generators. Okay, because by repeating application of 0 0 0 you don't get the element 1, that is one case. Similarly by adding 0 0 you don't get 2, and by adding 0 0 you don't get 3, that means 0 is not a generator. Now similarly if you take 2, if you take 2 plus 2 plus, you have to go on continue, of course you will get here 0. 2 plus 2 if you repeat 2 times you will get 0, but 2 plus 2 plus 2 if you add, you don't get 1 here. Okay, by repeating application of 2 you don't get 1. Similarly 2 plus 2 means it is not possible to get 3 also. Okay, that means that's why the 2 is not a generator. Okay, if you get 2 by repeated applications you get 0, 1, 2, 3. If you generate, then that will be the case that you get 2 as the generator, but it is not possible to get, that's why 2 is not a generator, 0 is not a generator, because by repeating that you don't get the elements of Z. So you have to get all the elements of Z four, not the single one. Then only you can say that is a generator. Okay. Now here you see, find the number of generators of the group G. A is equal to A square, A cube, A to the power 4, A to the power 5, A to the power 6 is equal to E. Now, by the definition of Z, it follows that A is a generator of Z. Okay, that is all obvious, because every element we are expressing as the power of A. Therefore, what we can say is, G is cyclic and A is a generator of G and G is generated by A. And its order is how much? The order D equal to 6 is there, because here A to the power n equal to E already. The order is D equal to 6. Now, how many elements are there? 1, 2, 3, 4, 5, 6 are getting here. Now, already you are taking one of the property here. The element A to the power K plus D is also generator of J if K, comma D equal to 1. That means KQ plus D, Ks plus dt equal to 1. Then you have K6 equal to 1. That means GCD of K6 equal to 1. That means a to the power k is a generator if and only if kd equal to 1, then you are writing k6 is equal to 1. That is GCD of k6 equal to 1, the meaning of this. Now, if you put k is equal to 5, is the only generator which is relatively prime to 6. Okay, which is only relatively, we have to take k6. If you take here 2, you get how much? 2, 6 means common element 2 is there. The divide, you can divide 2, 6, the common you are getting here 2, you will get here. That is the common element 2 you get relatively. If you take 5 and 6, they are relatively prime. There are no divisors that containing 5 and 6. You see here divisors of 5 and 6 are there, then they are relatively prime. There is no common element, the common divisor here. Now, what we can say, e to the power 5 is also one only generator of the other than e. Okay, that means you see here a is one generator and a to the power 5 is another generator. Okay, that means two generators are existing here. One is a, second one is a to the power 5. How you have to find out means, you see they are relatively prime here. K is equal to 5 means we are getting here relatively prime. Then you can say that here k is equal to 5 means we are getting a to the power 5 as the generator. That is the one way of finding the generators. Okay. Now, find the number of generators of a cyclic group of order 10. Find the number of elements of cyclic group of order 10. Now, here just to see, already taken the theorem, you see that property, the cyclic group of order n has pi of n number of generators. Already you know pi of n means less than n number of generators, less than n and relatively prime to n. This is called pi of n. This is called Euler's function. Okay. Already taken that pi of n equal to n into, you can write this as 1 minus 1 by p1 into 1 minus 1 by p2, so on to 1 minus 1 by pr already. Now, what are the p1, p2? They are the distinct prime factors of n. Now, any number you can express as the product of prime numbers. Already know that. Is it not? You can express any number as the product of prime factors. Okay. Now, if you take n equal to 10, here you can say 2 into 5. 2 is a prime number, 5 is a prime number, because the divisors of 5 or 2, they are two is they themselves, and then one is the only factors they are existing here. Now 2 into 5 you got. How many you got here? Two terms you got here. P1 equal to 2, P2 equal to 5 are getting. If you take first one as P1, second one as P2, you get two values you are getting here. Now what we can write here? You see the formula here, n is there. What is n here? N is equal to 10. Okay, the order of that is equal to, here you are getting here 10 you are writing. Okay, n equal to 10, and 1 minus 1 by P1 means here P1 equal to the first number, P2 equal to 5 you are writing. Now, if you simplify this, you get here pi of n equal to 4. Now, we can find how many generators are there for the cyclic group of order 10. The number of generators are 4 are there. Okay, the number of generators are 4. Now, similarly, if you take the cyclic group of order 60, we can find out the generators. You see n equal to 60 here, and already you know from the last theorem, you can say the number of generators of cyclic group of order n is pi of n, and here you can add pi of n equal to n into the same file you are adding here. You see pi of n equal to n into 1 minus 1 by p n, 1 minus 1 by p2, so to 1 minus 1 by pr, where p1, p2, so on to pr are the distinct prime factors of n. Now, 60 you have to express as the, product of primes. You see, this is the way you have to express the product of primes. Okay. Now, what we can write here, the basis is, you see the basis 2, 3, 5 is there. You can take this is p1, this is p2, this is p3. That means p1 equal to 2, p2 equal to 3, p3 equal to 5. That means three numbers are there. The base, that is prime numbers are 2, 3, 5 are getting. Now 1 minus 1 by p1 means 1 minus 1 by 2, 1 minus 1 by p2 means 1 minus 1 by 3, 1 minus 1 by 5 is 1 minus 1 by P3. Now, if you simplify, you will get here pi of n equal to 16. By simplification, you are getting 16. Okay, this is the number of how many generators are there for number of 60 here. See, the number of generators are 16 you are getting. Okay, now cosets. Okay, here with this the order of cyclic element, cyclic group of here you see what here already taken here the number of generators. Z5 is what? Z5 is the 0, 1, 2, so on to n minus 1. Okay, residue modulo of group, residue addition modulo, residue. Here Z5 are getting 0, 1, Zn is getting 0, 1, 2, so on to n minus 1. Z5 is the you can have 0, 1, 2, 3, 4 are the elements. Okay, and here the binary operation is addition, therefore 0 is the identity element. Okay, 0 is the identity element. Okay.